All right, on the previous slide, we learned that chromium fluoride will precipitate when the concentration of fluoride ion is equal to 8.7 times 10 to the minus 4 molar. So let's find on this slide what it'll take for calcium fluoride to precipitate. So CaF2 solid in equilibrium with calcium ions, aqueous, plus 2 fluoride ions, aqueous, and our KSP expression will be calcium ions times fluoride ions squared. Let's see, KSP for calcium fluoride is 5.3 times 10 to the negative 9, and calcium ion is 0.1 molar, and then fluoride is what we are looking for. So I'll take this expression and divide both sides of the equation by 0.1, which will give 5.3 times 10 to the negative 8 is equal to the fluoride ion concentration squared. And so if I take the square root of both sides, I'm going to get 2.3 times 10 to the negative 4 is equal to the fluoride ion concentration to make CaF2 precipitate. All right, let's compare that number to what we found for chromium fluoride. And it turns out that this is a little bit lower. They are both times 10 to the minus 4. So then we have to go and compare the coefficients that are in front. We've got an 8.7 versus a 2.3. So as we are gradually increasing the fluoride ion concentration by adding sodium fluoride into the beaker, the first thing that's going to start precipitating out is calcium fluoride. So let's go ahead and answer that. CaF2 precipitates first. This example is another very common type of question that gets asked with these precipitation reactions. We're going to take two different solutions that both have completely dissolved up ions, completely soluble, and then when we combine them, the cation from one solution forms an insoluble salt with the anion from the other solution. So we need to figure out what Q is once we have combined the two solutions, and then compare Q to K to see if it'll precipitate or if it'll all stay dissolved up. There's an added twist on this kind of problem in that we're combining two solutions so they dilute each other. So for instance, in this case, we are adding 750 milliliters of one solution to 300 milliliters of the other solution. So our total volume will be 1050 milliliters. And in our dilution calculation, that'll be our V2. So as an example, to figure out our oops, I don't think I ever stopped and actually read this whole problem to y'all. So a solution is prepared by adding 750 mils of 4 times 10 to the minus 3 molar cerium nitrate to 300 mils of 2 times 10 to the minus 2 molar potassium iodate. Then we're trying to see if cerium iodate will precipitate out. So cerium is coming from the cerium nitrate and iodate is coming from the potassium iodate. And so cerium iodate is the insoluble salt, and so its KSP reaction produces cerium ions plus 3 iodate ions. And so we'll need to calculate what the concentration of each one of these ions is after dilution, and then plug that into our Q expression, and then see if how Q compares to K. So for the dilution issue, for cerium, M2 will be M1 V1 over V2. Well, we already calculated V2 is 1050. The initial molarity of cerium is 4 times 10 to the minus 3. And its initial volume is 750 milliliters, and that's all going to be divided by 1050. I'm being very sloppy. I really should be writing all the units in here. Milliliters cancel with milliliters in the top, leaving just molarity for the unit. And let's see, after I run this through my calculator, I have a molarity for cerium of 2.86 times 10 to the negative 3 molar. If we consider the dilution for iodate, M2 will be M1 V1 over V2. And M1 for iodate is 2 times 10 to the negative 2. V1 is 300, and then V2 is 1050. And so if we'll run that through the calculator, we're going to end up with an M2 value of 5.71 times 10 to the negative 3 molar. All right, so let's plug this into our Q expression. Q will be cerium multiplied by iodate cubed. And so cerium is 2.86 times 10 to the negative 3 molar, and iodate is 5.71 times 10 to the negative 3 molar, but we've got to cube that one. I already have that number shown on my display, so I'm going to raise that to the third power. And then I'm going to multiply that by 2.86 EE3 negative, and I end up with a value for Q of 5.34 times 10 to the negative 10. So 5.34 times 10 to the negative 10 for Q. If we compare that to K, this is just barely bigger than KSP. They both have the same power of 10, so we have to compare the coefficients out in front, and 5.34 is bigger than 1.9. So this is telling us that Q is bigger than K, and so that means that cerium iodate will precipitate. That's our bottom line. Yes, it will precipitate from solution. All right, so our objective was to explain this relationship between Q and KSP. If Q is bigger than KSP, precipitation occurs. So we'll write that out. If Q is bigger than KSP, precipitation occurs. If you combine two solutions and Q is less than KSP, then there's no precipitation. And for selectively precipitating ionic compounds, we saw in that example with calcium and chromium fluorides that, gosh, I believe the conclusion was calcium would precipitate first, but I could be wrong about that. Go back and double check what the numbers said. But we can create conditions so that one ion preferentially precipitates, leaving a different ion present in solution. And we're going to explore that a little bit more closely in a later video as well.